I wasn't here last year, but I know that there was a demo called Little Bit Synth Kit as a physically embodied domain-specific functional programming language. And it was actually the title that got my attention, because I thought, well, could we really have a physically embodied programming language, like a programming language with physical bits, but ultimately compiles to LLVM? So that's what I was wondering. So here's the syntax for my language. Okay, and the other starting point was, this is what I want for Christmas. Unfortunately, they cost about, I don't know, this is probably about $100,000 worth of equipment here, but it's a modular synthesizer, so there's lots of bits and pieces that are connected by patch cables with lots of knobs, and they make all kinds of weird and wonderful noises. So I warn you, I'm not a musician. I have no musical ability whatsoever, but I do know how to make noise, and I'd love to make noise with one of these. So this is my starting point. Well, I'm just going to dive in and show you the stuff I built, and then I'll just pick random subtopics about it to talk about. So here's my interface. I'm terrified this might not work because I'm very bad at electronics, okay? But it still seems to still be here in one piece. No, that would be cool as well. That will happen next. So anyway, so this is what it looks like. Okay, with a USB interface. This is whiteboard, by the way, because it's reconfigurable. I can use dry erase pen to configure the markings. So I will plug it in. And let me see. It takes a few steps to start it up. So this display is a different size to what I'm used to. I'll say something about why I have to start this many executables to get it going. There's quite a few. Okay, this is the tough bit. This is where it actually talks to the hardware. This bit's written in Python. Sometimes it doesn't run. Sometimes it runs, but it does the wrong thing. Talking to hardware is difficult. Come on, I've done this 100 times. It might... Oh, okay. I've never seen a problem like this before. I've never had a bus error from this thing. Never had a bus error. That's completely new to me. Let's try this. That looks like it's working. I did things in the wrong order. It might not work. Okay, hang on a second. I did things in the wrong order. Let me start again. It's definitely behaving weirdly. Let's start that.
We believe it's live now.
Yeah, you do believe it's live. Okay. I have graceful fallbacks, okay, for this presentation, depending on how much works. That looks like it's working. Oh, I know what I've done. Okay, let's start again. Start again. Sorry about this. I actually want to run the example, not just the blank thing. Okay. So now I know what to do. This screen's tiny. It's going to be tough to do this. Yeah, okay, that's good. Yes. Okay, this looks good. So this is now a representation of the hardware. Okay. So, well, that was just the first trial. The second trial was, does it actually really produce audio? So there is a section on my panel here that says VCO, which is voltage-controlled oscillator, and there's a little bit with a sine wave underneath. So I plug the cable in there, and I plug that to my output, and I don't get any audio. There we go. So there's an envelope on there, and it's playing a sine wave with an envelope. Okay, so why is this at farm? This is just a modular synth, okay? Well, every time I pull out a cable or plug a cable in, it's actually taking a complete graph which is describing the synthesizer and it's actually synthesizing C code, and then compiles and links that and loads that shared library in, and then starts using that for audio synthesis. So apart from that, just about all of it's written in Haskell. The front end, the GUI is written in Haskell, and the code generation is written in Haskell. And there's a few little bits and pieces written in C. Well, let's do some programming. So, okay, well, sine waves are fun, but how about sawtooth wave? So there's a filter going on here, and there's a knob called VCF, which is a voltage-controlled filter. So we can change that. But there's another voltage-controlled oscillator, so let's throw one of those in. Well, it's just the same thing twice as loud, but I can detune the other one slightly. No, that's a sine wave. I want two sawtooths. Yeah, there we go. That's more like it. Okay, and you know, twiddling the knobs is sometimes too much hard work, right? You want to make it procedural. So there's a low-frequency oscillator that outputs a sine wave. So I could plug that in to the filter. Can you still hear me? Yes. Don't go to sleep on me. And I could probably go on forever, so I'm going to stop doing that for now. That works, and now I'm not stressed anymore, okay, because I can just do the rest with software. Okay. So what's going on? I think I've said all of this. So yeah, it's generating C code, so it genuinely is a compiler. And it talks to various things. You can plug in MIDI devices, and you can talk to it using the OSC protocol and use cables and knobs. So here's an overview of how I built the code. There's this core thing called Moodler, which basically is a kind of a standalone thing. So I've written things as separate executables. It really helps with having things not interfere with each other. So the Moodler thing is a separate executable that receives OSC commands and basically does the code generation, that does the audio synthesis. And there's a whole bunch of other things like the graphical UI, the physical hardware, and MIDI devices that all talk by OSC to the core Moodler. That makes things much safer. If one thing breaks, the others don't, and so on. I lost track of what time we're at, but I suspect I won't have time to go through my decision process for various languages that I used, so I'm going to skip that. Just say something about the code structure. So this is Moodler. It's code structure. Basically, Moodler is written in Haskell. I'm generating C code. The UI is written in Haskell. So as a programmer who wants to develop, well, as a user really, who wants to develop things, there are two places where you can insert plugins. You can write plugins that are in a language that isn't quite C, and I'll get onto that. And you can also write GUI plugins. So all the elements in the GUI, which you haven't seen yet, I should actually run that so you can see, are all plugins written in Haskell. So during runtime, during its run, you can write plugins in Haskell and just run them and create things on the fly. As I forgot to show the user interface, I may as well just show that quickly. Yeah, that's okay. Okay, so this is a representation of the thing I have here, but we can look inside. We can flip that over and look on the back side. Okay, well, I do have a zoom operation. See, it's just like that picture. This is what I wanted for Christmas. In fact, I can zoom out even more. So there's a lot of components here. I spent a lot of time writing all of these. So there's oscillators, low-frequency oscillators, high-frequency oscillators, noise generators, filters. There's things that aren't here as well, arpeggiators. I learned a lot of stuff because I didn't know about audio about a year ago. And you can just take anything, plug it into anything else. Some of these things are actually built from more pieces if I look inside. So that VCO is actually made of a whole bunch of different synthesizers, sine wave, triangle wave, whatever. These are all anti-aliased audio generators as well, which took quite a bit of time to figure out. So that stuff's all written in Haskell. I was quite surprised I could get the performance, but I did somehow. Okay, So the audio stuff, this is where, so I haven't been very high-minded here. I thought I'd use something a bit like C. So I wanted to write a programming language to generate the basic audio. And I'm really lazy. So if I'm going to develop a whole language, I'm going to have to write a parser for it and all kinds of stuff. So I didn't write a parser. The syntax for this language just happens to be identical to the syntax for C. But the semantics are different, okay? But it means I could just use... There's already a C language parser on Hackage somewhere, so I just use that. So this is for a voltage-controlled amplifier, which basically just multiplies two signals. So the function exec is what does the work. Unusually, one thing that makes it different from C is that the output is specified in the arguments to the function. So it looks like it's got 3 arguments, but it's actually got 2 arguments going in and 1 coming out. And the attribute thing is a Clang extension that allows me to set a default value. So if a cable's not plugged in, it will use the value 1. So basically, all Moodler does is take these little fragments of C and mushes them all together into one big loop and does some alpha conversion so you don't get clashes in the names. And that's it. But it produces fast code. This is how the code kind of... Well, if you just write a module like this in MSL, as I call it, Moodler shader language, I come from a graphics background, right? It will actually generate a little UI component for you. And that's actually a piece of Haskell code to generate. So it's actually code generation on code generation going on here. So it generates some Haskell code to generate the UI component, which is what we have at the top. And if you feel fancy, you can actually take that code and edit it and make it look a bit nicer. So actually the VCA that you get in the UI is actually the lower one. But if I hadn't done that, then you just automatically get the upper one by default. And this is what those plugins look like, the UI plugins. They're very uninteresting. It's just an imperative description of what pieces, inputs, outputs, which image to use for the module. Here's a minimal example. MIDI input. You can have lots of MIDI inputs simultaneously, and plugging into an envelope generator, an oscillator. That actually turns into a piece of code. The code generator produces something like this. So you can see it's very simple, it's just a loop. It's filling a buffer of 256 stereo samples. So that example where I showed the voltage-controlled amplifier that just doesn't multiply, the yellow line is basically where that line of code went. It's just the same as the original code, but with different variable names. The envelope and the saw wave generation, they're quite complicated, so they haven't been inlined. They appear as separate functions. I could show you what they look like, but I won't. Not enough time. Okay, so some random topics about how I wrote this code. Anyone who knows me knows that I like to play with all kinds of random abstractions and things in Haskell. But I hate user interface programming. I'm just terrible at user interface programming. And I am just completely old school. I want to program like it's basic back in the 80s. I want to call a function that gives me an event, and then when I've got that return value, I then want to carry on with my code. I don't want some silly nonsense where the OS calls me in some random callback thing on some object somewhere. I have no idea what's happening. I just want to be able to read my code. So I'm not going to give too many details, but typically what happens is the OS is running along, then it calls your callback, and then you return back to the OS. So I have a little trick. I don't have time to describe it now, I think, but I have a trick called reinversion of control, which allows you to take control again. So you can write code that looks exactly like you are calling the OS and asking it for an event, but that's not really what's happening underneath. But that allows you to write very linear code. Normally, I wouldn't want to do that, but for a user interface, this is the definition of imperative. I am giving the computer commands, and then it's doing something. And I just wanted to write imperative code. So if you look it up on the web, you'll find on my blog, I talk about reinversion of control. You can do it with continuations or free monads. I just happen to use free monads, but I'll skip that in the interest of time. So how does the hardware work? There's a couple of Arduinos on the back. Each one produces, on output, a square wave. There's a unique square wave, and the inputs just listen for square waves, and then they can identify which wires have been plugged in. It's as simple as that. It was quite cool when debugging the hardware because each of the live wires had a unique signature. So if something was accidentally touching something else, I could actually figure out what was going on just by listening on those wires. It was helpful. Here's an example where cables are kind of useful. Very briefly, if you're playing with reverb, synthesizing reverb is actually quite a black art. It's quite tricky. If you want to do it completely synthetically, which I did. And one approach is basically to take multiple audio channels and send them around on a loop with a matrix that mixes up all the channels and a bunch of delay lines. And the point is, when you have a mixture of all of those, once you've gone a few times around the loop, you've got so many different delays going on, you've really smeared the sound out, which corresponds to all the different reflections you might get in a room like this. And if you look inside that matrix, often it's a simple geometrical operation, like a reflection operation, but also you permute the inputs going in, just to mix things up and give a bit of variety. So it was kind of fun to play with that because there's a nice natural way to represent permutations, and that's having a bunch of cables going from one inputs to outputs. So that's an example where it's kind of fun to use cables to explore a space that's otherwise kind of tricky to explore. Okay, so how much time do I have left? Can I
3 minutes.
Can I do like a...
Questions, so tell people what to ask you.
Okay, let me just try and run... Well, I'm going to thank my friend Barnaby for writing the port audio version and an oscilloscope, which I can't show because I can't compile it today. Let me just try and run the absolute... You know what? I can't run the minimal example. Let me run some other examples. This is just gluing C code together. The C code could be any kind of C code. Any of you guys know what a one-line symphony is? Okay, so if you know and you like that kind of thing, you'll enjoy this. Otherwise, you should probably cover your ears at this point. So it's really awesome. Basically, you can have a timer which goes up by one, I don't know, every 48,000th of a second or something like that. It's an integer. And if you perform integer operations like shift right, shift left, and all that kind of stuff, it turns out that you can actually sometimes compose a piece of music that way. But this is a perfect test bed for exploring that kind of thing. So here we go. So this is just, if you listen, there's actually structure going on here. It's not random. Because music kind of has a natural binary structure, at least popular music, both in the terms of pitches, which go in octave scale, but also there's just the structure of popular music stuff. So anyway, this is kind of fun to play with. People don't get modular synths because they want to make a beautiful piano or clarinet. They want to make noise, okay? And the cables are green to indicate that these are actually integer passing through the system. And at the end, it gets converted to actual audio samples. So. Okay, I think I should kill it now. Okay, great. I think I've come to an end now. So. Oh, yeah.
So I'm wondering if you've tried connecting this to a radio instead of to speakers.
So believe it or not, I have actually considered doing that, and I might do that. I've played with GNU Radio. I bought one of those $10 software-defined radios. I got it to work. I actually rather than just use examples off the web, I did actually write my own FM radio. And I think this would actually work perfectly well. I don't think there are any issues. The only reason for not doing it this way is that there doesn't seem to be much room for creativity there. I mean, I built an FM radio, and what am I going to do with it? I can't really tweak the parameters. It would just make the sound bad, that's all. So that was the only reason why I haven't done it. But I totally think it would work, and I think the speed would be no problem. I mean, it needs to be able to do maybe a couple of 100,000 samples a second, and this code has no trouble doing that. So, yeah. Well, I saw yours first.
Maybe I'm being sick, but the point of the flight case is just a complicated way of deciding which wires it
Yes. Although I actually quite like it because there are some advantages to physical things. And also, so one thing I quite like is that I've been kind of heavily influenced by this typed programming thing where you do things correctly. And it's quite nice to actually have something that's not a computer because then it sort of invites you, what happens if I plug this in here and do stuff that's not... In fact, I've deliberately written the code so it doesn't really do type checking, and you can connect an integer to a float or whatever, and things will still work. So I actually quite like that aspect of it. It's kind of liberating to not have the computer. I've had it here now for a demo, but otherwise not. But yeah, it's just fun to play with cables.
When you were plugging different wires in, there wasn't much or any noticeable latency from the recompilation. Did you have to use any particular clever tricks to be able to compile and code quickly enough?
So there's two things you could call latency. One is the latency of switching over to the new audio generator. It's probably about a quarter of a second. Clang is fast. I mean, that's why I chose C. It's incredibly fast. I was just astonished. But the actual switchover, that basically takes zero time. There's a DSO in memory that's generating samples. And then as soon as it's finished one batch of 256 and it knows that the next DSO is ready, it's just jumping to the next one. So there is no delay. So you get a clean switch over. In fact, if I was feeling really fancy, I'd interpolate between the two. But yeah.
It didn't show that you were patching the cable on the interface?
No, the reason why is just because there's this core thing that does all the work, and all the other things just send it messages, but it's all unidirectional. There's no messages going back. I did think about trying to hack that in the last couple of days, but that's kind of risky before a conference, right? So, yeah.
It would be really cool technology.
I think it would actually. Yeah, I totally agree, and I will try and do that. Yeah. Okay. Great.